Have you ever wondered how databases and search systems stay so incredibly fast? I mean, even when you're just throwing massive amounts of constantly changing data at them? Well, a big part of the answer lies in this really clever, self-correcting data structure, the AVL tree.
So, take a look at these two trees. On the left, you've got this perfectly symmetrical binary search tree. It's beautiful, right? But then on the right, you have something that's, well, it's not quite perfect. And yet, it's often just as fast and way more efficient to maintain. So what if I told you the secret to high performance isn't being perfect, but just being good enough?
In this explainer, we're going to break down exactly how this works. We'll kick things off with the problem of unbalanced trees, then get into the simple rule that AVL trees live by. We'll see the magic of rotations that fix them, cover the 4 main scenarios you'll run into, and finally, we'll talk about why any of this really matters for building fast, reliable software.
Okay, so first up, let's set the stage. Why do we even need to worry about balancing a tree in the first place? What's the big deal? Well, imagine you're building a digital phone book, and you start inserting names in alphabetical order. Adelson-Velsky, then Landis, and you just keep going. In a standard binary search tree, a BST, each new name is greater than the last one, right? So it just gets added to the right, and the next one to the right of that, and so on. You don't get that nice, bushy, efficient tree you're hoping for. You get a long, spindly chain, and searching this thing, it's just as slow as scanning a list from top to bottom, which completely defeats the purpose of using a tree.
This exact problem is what AVL trees were invented to solve, and they do it with one brilliantly simple rule.
It all comes down to a little something called the balance factor. For any node in the tree, any node at all, you just take the height of its left subtree and subtract the height of its right subtree. For the tree to be a valid AVL tree, that result has to be -1, 0, or 1. That's it. That's the whole rule. Now, just one quick note for the math. If a child doesn't exist, we just say its height is -1.
Let's see this in action with a nice, healthy tree. Let's focus on the root node, which is 7. Its left subtree has a height of 1. Its right subtree has a height of 0. So what's the balance factor? Well, its left height, 1, minus right height, 0, which equals 1. And that is totally in our acceptable range of -1, 0, or 1. So this node is balanced. Everything's good.
Okay, but what happens when we break that rule? Look at the node highlighted here in red, number 6. Its left subtree has a height of 1, but it doesn't have a right child. So we use that special height value of -1. Now the math becomes left height 1 minus right height -1, which gives us a balance factor of 2. Uh-oh, that is outside our allowed range, and because of this one single node, the entire tree is now an invalid AVL tree.
All right, so we can spot an imbalance. But how do we actually fix it? This is where things get really cool. The solution is this elegant, almost mechanical process called a rotation.
We found a node with a balance factor of 2, or maybe -2. The tree is officially out of whack. The question is, what are we going to do about it?
Let's take a look at this example right here. Node 60 is our problem child. You can see its left subtree has a height of 1, but its right side is non-existent, so that's a height of -1. That gives node 60 a balance factor of 2. It is way too heavy on the left. The fix for this is called a right rotation. Now, it might sound complicated, but it's really just a couple of pointer changes. The left child, node 30, is going to pivot up and become the new root. Its old parent, node 60, is going to swing down to become node 30's new right child. And that in-between node, 40, it just gets neatly reparented to make sure the search order stays correct. And boom, look at that. It's so satisfying. With one quick rotation, the tree is right back in balance. Every node's balance factor is correct, and, this is the most important part, the binary search tree property is perfectly preserved. Everything to the left of our new root 30 is smaller, and everything to the right is larger. The tree is fixed.
So that rotation we just saw was the fix for one specific kind of imbalance. But it turns out there are 4 distinct patterns we need to have a strategy for.
So here's the game plan. After you insert a new node, you walk back up the tree from that new node all the way back to the root, and you check the balance factor of every single ancestor along that path. The very first one you find that has a balance factor of 2 or -2, that's your pivot. That's the node where we need to act.
Now, when a tree gets too left-heavy, it can happen in 2 ways. First, on the left, we have the left-left case. You see how the nodes kind of form a straight line? This is the easy one. It's fixed with that single right rotation we just saw. But now, look at the right side. The left-right case. This one's a zigzag. A single rotation just won't fix this mess. It needs a two-step move. First, a left rotation on the child node to straighten it out, then a right rotation on the original problem node to balance the whole thing. And you know what? If the tree is heavy on the right, the logic is an exact mirror image. On the left, you've got the right-right case, another straight line fixed with one clean left rotation. And on the right, you have the right-left zigzag. You can probably guess the fix by now, right? It's that double rotation again. First, a right rotation to fix the kink, then a left rotation to restore the balance. And that's it. These 4 cases cover every possible imbalance you could ever run into. So, we've gone through the problem, the rule, and the fix. But at the end of the day, what is the big payoff for all this clever rebalancing work? Why go through the trouble?
Well, this is exactly why it matters. With a standard binary search tree, your performance is basically a gamble. In the worst case, like our phone book example, your searches slow down to O of n. That's linear time, which is terrible. But an AVL tree, it gives you a guarantee. Because it keeps its own height in check, your operations are always a speedy O of log n. It's the difference between unpredictable and rock-solid reliable.
So here's the key takeaway. AVL trees make a very small trade-off. Yeah, they do a tiny bit of extra work checking the balance and sometimes doing a rotation when you add data, but what you get in return is a huge ironclad guarantee. Your tree will never become inefficient. Your searches will always be lightning fast. You could even say they're self-healing data structures. They literally detect a problem and fix themselves.
And this isn't some newfangled idea either. This was all laid out way back in a 1962 paper by the 2 inventors the tree is named after, Adelson-Velsky and Landis. I mean, this foundational concept has been a cornerstone of computer science for decades.
Which kind of leaves us with a final thought to chew on. If a data structure can be designed to automatically find and fix its own problems to stay efficient, what other self-healing systems are running silently in the background of the technology we depend on every single day?